I'm going to show you my tools that should get you through almost all of the types of balancing acts that you'll be asked to do. But this is all about obeying the law of conservation of mass, how we balance equations. And as I'm doing this, I'm going to show you different examples. And in each case, I'm going to also use that opportunity to highlight how we classify certain reactions. For example, this reaction of sulfur dioxide reacting with molecular oxygen to give us sulfur trioxide. This is what we would call a combination reaction. It's where we have two materials, A plus B, and they come together to form AB. Just in a general sense, it's what we call a combination reaction. Here's another one down below. Molecular nitrogen reacts with molecular hydrogen to form ammonia. That's also a combination reaction. Now, you've been learning throughout this semester how to name things, how to write the molecular formula of them, and how to put them in the context of a proper chemical equation. You not only list the proper compounds by their chemical formula, you also have to put what their state of matter is. So in this case, we would put this is in the gas phase, that's in the gas phase, and that's in the gas phase. You have a reaction arrow that shows reactants on the left are reacting to recombine and form products, which is on the right-hand side of the arrow. Right? All of these are the components of a properly written chemical equation. All right, but we also have to balance this equation. So there's several ways to go about doing this. And this first one for up here is fairly straightforward. We want to just make sure that the atoms are the same. The number of atoms of each element are the same on each side of this reaction. We have one sulfur on the left-hand side. We have one sulfur on the right-hand side. So if I just look at the sulfurs, they're balanced. But if we look at the oxygens, well, in SO2, we have two oxygens. And in O2, we have two oxygens. So there's 4 oxygens total on the reactant side. And on the product side, we only have 3. That's what the subscript is telling you. You remember now how to interpret the subscripts, right? The subscripts tell you the molar ratio of the atoms within a compound. In SO2, for every 1 mole of sulfur, there's 2 moles of oxygen. In SO3, for every 1 mole of sulfur, there's 3 moles of oxygen. That's how we interpret these symbols, right? The subscripts. All right, so we need to balance this. Now, this one might seem like it's easy, or it might seem like it's difficult. Sometimes you can get these with just trial and error. I'm going to show you some tools, and here's the first tool that kind of gets you through something where you've got an even number on one side and an odd number on the other, and we need to balance this. We're going to balance this by putting in coefficients in front of each compound. Okay? Now, if I were to put a coefficient in front of the SO3 to try to adjust the oxygens, because I have 3 on the right-hand side, that's going to mess up the balancing that I already have for the sulfurs. Ideally, you want to try to only adjust those compounds that only have that element in it that need to be adjusted, if you can. And in this case, we have molecular oxygen right here by itself. So if I can adjust the molecular oxygen to satisfy the balancing for the oxygens, then I don't have to worry about adjusting the sulfurs. Now, how can I do that? What coefficient might I be able to put right here that would balance the oxygens? It's a bit of a trick the way I'm asking you this, but what do you think? 1/2. That's what I'm looking for. All right. I told you it was kind of a trick. Ah, see, the light bulbs are starting to go off. If you put a 1/2 here, look what happens. If I had 1 mole of O2, how many atoms of O2 is that? 2. So if I have 1/2 of a mole of O2, how many atoms of oxygen is that? It's just 1. So if I put a coefficient of 1/2 here, that actually now gives me 3 oxygens on the left-hand side and 3 oxygens on the right-hand side. So this is now obeying the law of conservation of mass. There is a problem with this though, because when we have coefficients in our balanced equation, they need to be whole numbers. They need to be integers. We can't have fractions, but that's okay. We'll get rid of that in just a second. But I want you to first focus on this and recognize that this is now effectively balancing. We are now obeying the law of conservation. Now we need to get rid of the fraction. How do we do that? Right. Now we just multiply everything by the denominator, and that gets rid of the fraction. So let's just multiply everything by 2. That's going to put a, whoops, that's going to put a 2 here, puts a 2 here. It gets rid of the denominator and puts a 2 here. We've just multiplied everything by 2. When you get to a more complicated one, using the fractions approach will always get you to the final answer much more quickly. All right, so I encourage you to try doing it that way, and I'll show you a few more examples of that. Yeah. What's the point of putting 1/2? Because we had to do that to get it balanced. So the question was, why put the 1/2 here? What's the point of that? Because once you put the 1/2 there and you know that this is balanced, now when we do the math to get rid of the denominator, everything stays balanced. Because by starting with the fraction and now getting rid of the denominator, that tells me I need a 2 here. This goes away. Here, let's just erase it now. That goes away. And this is a 2. All right. So it may be more obvious when we get to a more complicated one later on. Right? But I want to leave all that in there. So you see I want the notes to reflect that we started it that way and got rid of the denominator here. So we end up with 2 to 1 to 2 in our coefficients. And of course, in this picture, the illustration, you can see there's 2 molecules of SO2, there's 1 molecule of O2, and there's 2 molecules of SO3, okay? And if you count up the atoms here, you can see that we have, on the left-hand side, we have 6 atoms of oxygen, and we have 6 atoms of oxygen on the right. We have 2 sulfurs on the left and 2 sulfurs on the right. Okay, so we'll come back to that shortcut with some examples later on. Here's another combination reaction. Nitrogen gas, let's put in our phases so that we have it properly written. Now for this one, we've got nitrogen and hydrogen. It's just 2 things to work with here. So what I typically do for these is you just kind of start with 1 and you balance 1. And in the process of balancing 1, you start to balance the other one. So in this case, I would just start with nitrogen. You have 2 nitrogens on the reactant side, and there's only 1 nitrogen on the product side. So we can balance that by putting a 2 in front of the NH3. Now the nitrogens are balanced. In the process of putting that coefficient in front of NH3, now I'll take a look at the hydrogen. That gives me 6 hydrogens on the right-hand side, because each molecule of NH3 has 3 moles of, or has 3 atoms of hydrogen. But now I have 2 molecules of NH3, so that gives me 6 atoms of hydrogen. So I need 6 atoms of hydrogen on the left. How do we do that? We put a 3, and boom, we're done. We're balanced. Now, of course, these are easy examples, okay? But in this case, we're sort of starting with 1, and we're just kind of bouncing back and forth. And each time we go back and forth, we're balancing 1 element or 1 atom type, and then we're balancing another atom type. All right, so in fact, let's get more complicated now. These look a lot more challenging, don't they? And before we start handling these, let me use this opportunity to tell you a couple of other categories of reactions. The general setup for a double replacement reaction is where you have a compound, we'll call it AB plus CD, and everything recombines. You see all the partners switch. This is typically what you'll see when you have ionic compounds interacting, where A and B is the cation and anion pair in an ionic compound. And CD is another cation anion pair in an ionic compound. So in fact, I'm going to put this here. Usually you'll see this with ionic compounds. And so now the cation and anion pairs are going to swap. So we always write this as cation first, okay? So now the A cation is going to be paired with the D anion, and the C cation is going to be paired with the B anion. Right? That's the general setup. But when you look at these things, it's like, well, look at the first thing. It's got silver, it's got nitrogen, and it's got oxygens. So how do you know that's an ionic compound? What's the clue? What's the clue that this is an ionic compound? I told you one way to tell for sure that it's an ionic compound, and that's when you have a group 1,2 metal on one side of the periodic table combining with a non-metal on the right-hand side of the periodic table. But what's another clue here? Yeah. Because there's a polyatomic ion. That's what we're going for here. Very good. What's the polyatomic ion? Well, I'm expecting now that you're going to start recognizing these. Nitrate is the polyatomic ion. You've got it there on the reactant side, and here it is again on the product side. Recognizing your polyatomic ions makes the balancing act for this so much easier, because many of you may have learned to balance equations by just counting up each individual atom type on the reactant side and on the product side, and then doing some crazy note taking and doing each one. This is so much easier if you recognize your polyatomic ions and then you keep them as polyatomic ions in this balancing act. Now, let me get rid of these. Let's put our phases here, all right? This is going to be silver nitrate in aqueous solution. This is iron. What is this? What's the charge state of iron? What's the charge on that iron cation? It's 3+. So is this called iron chloride? Or is it called iron 1 chloride, iron 2 chloride, iron 3 chloride, or iron 4 chloride? Show of hands with your numbers. Should be 3. Iron 3 chloride. Very good. And we show that with the Roman numeral 3. And this is an aqueous solution. And you may have remembered doing this experiment in lab when you have the silver cation combined with the chloride anion. It's not an aqueous solution. That forms that milky white precipitate. All right. We're going to be paying more attention to this when we get to the next chapter. For now, we're just going to be focused on balancing this equation. And to balance this equation, it becomes trivial if you keep your polyatomic ions as polyatomic ions. When these are an aqueous solution, they don't dissociate further into nitrogen and 3 oxygens. It stays together as the polyatomic ion. That's why when we did the Lewis structure of the nitrate ion in the last chapter, we did it as, it's basically a molecule. There's covalent bonds. It just happens to be an ion, okay? So it's a molecular ion. It's an ion of a molecule. So let's now balance the nitrates. How many nitrates are on the left-hand side? No, there's one nitrate. It's right here. There's only one NO3 minus on the left-hand side. How many nitrate ions are there on the right-hand side? There's 3, okay? So I'm not gonna count the oxygens here. I'm just counting the nitrate ions. There's 3 on the right, so I need 3 on the left. So I'm gonna put a 3 here. Now the nitrates are balanced. In doing that, I now have 3 silver cations on the left. I need 3 silvers on the right. So we put a 3 here. In putting the 3 on the silver chloride, that now gives me 3 chloride ions on the right. And how many do I have on the left? I have 3. Okay, so the chlorides are now already balanced for us. Let's take a look at the iron. We have 1 iron on the left, 1 iron on the right. So boom, we're done. Yes, question. Does it also, oh, great question. I'm glad you asked that. So when I said that there were 3 nitrate ions on the right, I was looking at this subscript here, okay? The NO3 is NO3, and that's in parentheses. Notice, by the way, that I didn't put parentheses around this NO3. That's because there's only one of them. If there's only one of them, we don't put parentheses around it, which is, now, if you have more than one, there's parentheses. That's another clue, by the way, that you've got a polyatomic ion because you're showing it in parentheses. So you won't always have the luxury, if there's one, that it's put in parentheses, right? But this question had more to do with, what does that subscript 3 do for the iron? Okay, this subscript 3 only refers to whatever's in the parentheses. This tells you this is still iron 3. Okay, this is iron 3 nitrate. So that's a great question. This 3 only modifies what's in the parentheses. Okay, so looking at the polyatomic ions made that much more easy to see. Here's another one, hydrochloric acid with magnesium hydroxide. And here, once again, we've got the hydroxide, that's a polyatomic ion. There's 2 hydroxide ions. The hydroxide ion is just OH minus. There's 2 hydroxide ions for every magnesium cation, because the magnesium cation is magnesium 2+. Now, in this case, though, we don't have hydroxide ion on the right-hand side. Okay, so it's a little more confusing here. But think about water as just HOH. You'll see why I'm doing this when we get there in chapter 8. All right, but that's H2O. We can still think of this as a double replacement. Okay, where now hydrogen is the cation and the hydroxide ion is the anion. So we still could do this as a double replacement. We've got 2 hydroxides on the left. I want 2 hydroxides on the right. So I would put a 2 in front of that. That's the same as putting a 2 here. Now, in doing that, let's take a look at the chloride ions. We have 2 chloride ions on the right and only 1 chloride ion on the left. So I need a 2 here. I got 1 magnesium on the left, 1 magnesium on the right. So we don't need to do anything there. So is this balanced now? It should be. Now, if you count the individual hydrogens, just to make sure, all right, we've got 2 hydrogens here and we have 2 more hydrogens there. That's 4 hydrogens. And here we have 2 times 2, that's 4 hydrogens. And the oxygens, we've got 2 oxygens here and we have 2 times, this is a 1, right? We have 2 oxygens there. So in fact, it is balanced. Okay, so by recognizing that H2O really is like HOH, and this is a double replacement reaction, this one's just as easy to balance. You see that? So these are both double replacements. All right, let's take a look at a different type. This is a single replacement reaction. This takes on the general form of A plus BC goes to, in this case, I've got this written as B plus AC. You've done this reaction too. Like in the copper cycle, you did a lot of single replacement reactions. These are typically where you have some solid metal is reacting with an ionic compound in aqueous solution. That ionic compound, the cation is a metal cation. And then things change places. And so now you end up with, this case, silver is now a solid. And this is copper. Is this copper 1 nitrate or copper 2 nitrate? How do you know it's copper 2? Because there's 2 nitrate ions and the nitrate ion is a 1 minus. There's 2 of them. Right. So this is copper 2 nitrate. And this is an aqueous solution. Right, let's balance this one. This one, we're keeping track of the polyatomic ions, so we're not going to split up our polyatomic ions. Let me just put a red bar. This should be pretty easy to balance now. Let's just go back and forth. Let's start with the copper. There's 1 copper on the left and 1 copper on the right, so we don't need to do anything there. There's 1 silver on the left, there's 1 silver on the right. We don't need to do anything there. So we got 2 nitrates on the right, though, and only 1 nitrate on the left. So we have to balance the nitrates. Now the silvers were balanced, but they're not anymore. So now I have to balance the silvers. And we're done. Okay. Pretty easy to do if you recognize your polyatomic ions. In the copper cycle experiment, you are also learning for the first time, I think, about oxidation and reduction. Most single replacement reactions are also oxidation and reduction reactions. Who remembers? What does oxidation mean? What happens when a metal gets oxidized? It loses electrons. So, something you might not know, when it's in the natural state, right? When you find an element in its natural state, it's always neutral. So, metals, when they're solid, they're neutral. I'm going to put a little 0 up here. So, elements in their natural state are neutral, meaning we have solid metals. They are neutral. So copper as a solid is neutral. It has the same number of electrons as it has protons. But copper in copper 2 nitrate in aqueous solution, what's the charge state of that copper cation? What is it? It's 2+. You even know that because I named it for you already. So what we have here is copper solid, which is neutral, is going to become copper 2+. Does it gain or lose electrons to become copper 2+? It's losing 2 electrons. So let's put them in here. 2 electrons. That's showing the oxidation in this reaction. Now you remember, hopefully, learning that you can't get oxidation without reduction. They happen hand in hand. So copper won't give up its 2 electrons to thin air, or water in this case. It's going to give them up because something else in that reaction wants them. In this case, the silver wants them. So the silver starts as silver 1+, but in our balanced reaction, we've got 2 silvers here, right? We have 2 silver plus cations coming right here. And they're going to become 2 silver solid atoms, which is neutral. So how many electrons do we need to have to get 2 silver plus cations to become 2 silver neutral atoms? 2. Let's put them in. Okay. If we were to add these up, the 2 electrons here cancels with the 2 electrons there, and we end up with 2 silver cations plus 1 copper solid metal atom will go and form 2 silver solid atoms plus 1 copper 2+ ion in aqueous solution. And look, that's exactly what we have in the balanced reaction. Okay. So what I'm showing you here in red, this oxidation and reduction, this is what we call half reactions. This is the oxidation half reaction, and this is the reduction half reaction. They both happen at the same time. And here I'm showing you the actual electrons. So anyway, that's a little preview. So let's get to some other types of reactions. These are combustion reactions. And I've got a couple of them here for you, right? But first, let's just talk about these in general. When you do a combustion reaction, by definition, you're combusting something, you're reacting it with molecular oxygen, okay? And in these examples, the material that we're combusting has carbon and hydrogen in them. Sometimes they'll have carbon and hydrogen and oxygen. Sometimes they'll have other materials in there as well. Magnesium, that didn't have any carbon. You combusted magnesium, and what did you make? Magnesium oxide, okay? But that's also a combustion reaction. It's just not one that contains carbon. These all contain carbon and hydrogen, okay? And what you get with that, when you combust something that contains carbon and hydrogen, something that we call a hydrocarbon, you get 2 classic components out. You get carbon dioxide and you get water. Okay. Let's go ahead and balance this one. Now here, where are we going to start does matter. Because if you try to start balancing this reaction with oxygen first, you're going to get a huge headache. All right. Look at the next one. What's the next? The next one's not a hydrocarbon. This is a carbohydrate. For all you biologists out there, you should recognize what that molecule is. What is it? It's glucose. Glucose plus oxygen gives you carbon dioxide and water. Okay. Many of you might recognize this equation, right? This is what's this called? You biology majors out there. Cellular respiration. Of course, we have to balance it. All right. You don't want to start with the oxygens because there's oxygen everywhere in the cellular respiration reaction. So one rule to keep in mind is always start with the elements that are present in only one compound on each side of the reaction. That's going to make your life a lot easier in this balancing. Save the ones that are in multiple materials for later. And usually what happens if you just focus on the ones that are present in one compound on each side, then in balancing those, you usually end up balancing the more complicated ones in the process. And that way you don't have to worry about it. And that's what's going to happen here. So let's start with the carbon. All right. We have 3 carbons on the left and 1 carbon on the right. So how are we going to balance that? Put a 3 here, right? Now in doing that, that does give us 6 oxygens there from the carbon dioxide, but I'm not going to look at oxygen yet. I'm going to save oxygen for last. Okay. So now let's go to the hydrogens. We've got 8 hydrogens on the left and only 2 hydrogens on the right. So how are we going to balance the hydrogens? Put a 4 here. Now the hydrogens are balanced. Now the carbons are balanced. Now we have to go to oxygen. We have no choice. Maybe they'll be balanced. Maybe they won't be, but let's see. We've got 2 oxygens on the left. And how many oxygens do I currently have on the right-hand side? I have 10, right? Because we've got 3 times 2, that's 6, plus 4 times 1, plus 4. So that's 10. So I have 2 on the left, 10 on the right. So how do I balance the oxygen? Put a 5, okay? So this one was easy. Oh, we forgot to put our states of matter. This is propane. For all you campers out there, propane gas with oxygen gas combusts to give you carbon dioxide gas, and H2O, we'll write that as gas. If we let things cool down, yes, the H2O would recondense into water. All right, let's do it for glucose. Let's start with, I just like starting with carbon. I don't know. Maybe it's alphabetical. I don't know. So we have 6 carbons on the left. We have 1 carbon on the right. So we can balance that with the 6, right? Again, I'm not going to go to oxygen. Oxygen's everywhere. I'm definitely leaving that till the end. So let's go to the hydrogens. 12 on the left, 2 on the right. Give us the 6. Now we have to go to oxygens. So right now, currently, I have 6 oxygens here. No, 6 plus 2 is 8. I have 8 oxygens on the left. Hold on a second. How many oxygens are on the right? 18. Because we have 6 times 2 is 12 plus 6. That's 18 oxygens. Yeah, what's your question? Okay, so the question is, shouldn't I have put a 3 here instead of a 6 for the carbons? The answer is no, because how many carbons for every 1 molecule of CO2, how many carbons are there? There's just 1. Okay, once again, this 2, just like it did with the stuff in parentheses, this 2 only modifies the oxygen. If it were to modify the carbon as well, you would have put parentheses around it. But I'm not going to show that because that doesn't make sense here. Okay. So how are we going to balance the oxygens now? We've got 18 on the right and 8 on the left. Before you start giving me your answers or your guesses, you've got 2 choices here. You can start playing around with the coefficients here and here. Okay. But if you do that, if we do anything to modify the glucose, we're now going to change what's already balanced for the carbons and the hydrogens. So this is where you want to take advantage of the fact that the last thing that we've saved to balance is present all by itself. So if we can solve the balancing of the oxygens by just modifying the coefficient in front of molecular oxygen, then we will have balanced everything. We won't have messed up the carbons and the hydrogens. You all see that? That gets back to the fractions. If you needed to use the fraction trick that I showed you earlier, that's where we would apply it now. In this case, we don't need to use the fractions, as you'll see, all right? Because we have an even number of oxygens on both sides. And in this case, oxygen comes in packages of 2. We can't split them up. So let's see if we can solve this now by just putting a coefficient in front of the oxygen, which means I'm going to forget about these 2. I only have 6 now. So what coefficient can I put in front of the molecular oxygen to give me, what do I need? I need 12 more, right? 12 more gets me 18. So we put a 6 here. And now it's balanced. And again, for those of you who are familiar with this reaction, you already know that it's 6, 6, and 6 for the coefficients. Okay? So there's a couple of rules there. Before I show you another example, let me summarize these steps, these rules that we've been doing here. So here I've saved myself a large space here. So there's a lot I'm going to write down here. I'll just warn you right now. Okay, so step number 1, we're going to start with elements that are present in only one compound on each side. Okay, and then we're going to sort of bounce left to right or side to side. And by bouncing, that means we're balancing each element at a time. While we're doing this, we're going to recognize what our polyatomic ions are. And when we do that, they remain as polyatomic ions in aqueous solution. In other words, we don't split them up, so we can just treat them as one unit. Instead of NO3, we can just call it X, and you just balance the X's. Okay, rule number 4, if they're present in more than one compound, so if an element is present in more than one compound on each side, we're going to save that one until the end. And usually when we do that, it will have ended up already being balanced by virtue of us balancing everything else first. Before you get to it, if you save it until the end. Okay, and then 5, if you have the element isolated in a compound, like O2 or N2 or H2, okay, use those for the final balancing step. Because that way, you make your final adjustment on that compound, you're not going to mess up all the balancing work that you did leading up to that. Okay? And then one more, use fractions to solve an even odd situation, which I'll explain what I mean by that in a second. And then get rid of the fraction by multiplying through. Yes, question? Yes, when you multiply through, that means that whatever's in the denominator, that's going to multiply whatever coefficients you already have placed prior. Yeah, and you'll see that. That's a great question. And you'll see an example of that right now. Okay, we've got oxygens everywhere, so almost everywhere. So let's save those till the end. Let's start with the carbon, because I like starting with carbon. 4 on the left, 1 on the right. So that gives us 4 carbons here. Let's now go to the hydrogens. 10 on the left, 2 on the right. So we put a 5 here. So far, so good. Now we got to look at the oxygens. We've got 2 oxygens over here. And how many oxygens do we have on the right-hand side? We have 4 times 2 is 8, plus 5 times 1. That's 13. Okay? This is what I mean by an even-odd conflict. We've followed all these steps, and we're saving the oxygens for the end. But now, to balance the oxygens, because it's molecular oxygen, we can't have an odd number, right? There's no way to put a coefficient in front of O2 that gives us a 13 in the end, okay? So this is where the fractions will help you. Again, there are other strategies, okay, but that's more kind of like a trial and error. Let's solve this with fractions. What fraction can I put in front of the O2 to give me 13 oxygens? Earlier, we put a 1/2, okay? And I explained to you that 1/2, right? Well, if I have 1 mole of molecular oxygen, how many moles of oxygen is that? It's 2, right? So if I take half of a mole of molecular oxygen, that gives me 1 mole of oxygen, okay? So we want 13 moles of oxygen in the end. So we need 13 halves for our fraction. If it's 13 halves of O2, how many moles of oxygen is it? It should be 13. But now I've got to get rid of the fraction. So now we multiply everything through by what's in the denominator. That's going to give us a 2 here. That gets rid of the denominator. That turns this into 8 and turns this into 10. So now we have the correct balanced coefficients here. And I'll just write them down. It's 2C4H10 plus 13O2 goes to 8CO2 plus 10H2O. And now if you count these up, you'll see 2 times 4 is 8 carbons on the left, and we have 8 carbons here on the right. 2 times 10, that gives us 20 hydrogens on the left, and we have 10 times 2, that's 20 hydrogens on the right. And oxygens, 13 times 2 is 26 on the left, and here we have 8 times 2 is 16 plus 10, that's 26. So it's balanced.